Hi, my name is Juan Suarez, and this is Physics 2211 Video Lab 2. In this lab, we will compare observations to our computational models that will account for drag and gravity when an object is going in motion and falling slowly from rest. Understanding some concepts like velocity and the effects of beginning conditions are the main goals of our model, and our experiment aims to study and simulate the motion of an object dropped from rest with the effects of gravity and drag. The most important principle that we will mention in this lab is Newton's second law, which you can see the various derivations of the equation above. F net equals the vector of momentum over time, and then you have the velocity updated formula in terms of F net. And in this lab specifically, we'll talk about two other forces, which are the force of drag, which can be air resistance, and the constant force of gravity that pulls objects down. To preview the lab, we can talk about this. Is the motion constant? Do external forces play a role? Does it go in a straight line? How does the position versus time graph look? And does the experiment line up with the coding? To answer those questions, the motion won't be constant due to gravity, and external forces such as drag and gravity will play a role in this experiment. It will go in a straight line because there is no net force applied horizontally. A position versus time graph will look more curved than the initial straight line we're used to seeing, and the experiment will line up with the code as all three versions will have that curved shape. The systems and surroundings of this experiment are as follows. The system is the object in motion, and the surroundings include the air resistance, the gravity, and the classroom. The initial conditions of our lab are as follows. The initial position starts at 1 meter of height, and it will travel to 0 meters vertically, and its direction is moving down, and its force is gravity and air resistance, which is a force of drag. What we will need for this lab is a camera, a ruler, the object in motion, which is a paper ball, and a tracking software like Tracker. The steps are as follows. First, we will video capture and analyze the information. We will record the motion of the object that was initially dropped from rest, and using that video, we will transfer it to the Tracker software to extract specifically the position versus time data. And then we will make two computational models, one with gravity only, and another one with gravity and drag. And later, we will graphically compare all three graphs presented above. Using the Tracker app, we can analyze first, how high we dropped the ball from, and secondly, how we can extract a position versus time graph. So this top one is the position versus time graph with every single point done using the Tracker app, which you can see that curved motion that isn't straight. And then in the second one, we can see each individual point that we plotted to get this. Using the starter code provided, we can code the force of gravity and the force of gravity with drag. So on the left side, we can see the code when we want to apply gravity, which the difference is that F net will be the mass of the ball times gravity times j hat, which would be in the y-axis. And then we change the velocity to ball vel plus F net times the mass of the ball divided by delta t, and everything else stays constant. For the drag, what we change is that we have two forces, which is one, the force of gravity, and two, drag, which is using the equation shown earlier. So we do the same thing except we add drag force, which is negative b, which is some constant, times the magnitude of the velocity squared times negative j hat. And by coding all of this, we have these graphs presented, which we can see all of them are very much parabolic. The first one, as we've already seen. And then drag is slightly lower than no drag because drag makes it slower and elongates the time, because if there was no drag, all objects would drop at a constant negative 9.8 meters per second squared. And we can see that comparison in the bottom left corner. Some sources of error that can be present include drag consideration, the video analysis, air resistance, and model limitations. Drag consideration because we don't have a very specific formula to find the drag. The video analysis will never be picture perfect, so the points could be realistically a bit more specific. Air resistance can always be a bit uncertain, and model limitations because there are better ways to show this proof. The question asked is which models predict terminal velocity, and what does it mean for the net force? There's two different types of graphs that we can see. The ones that we show are position versus time, but as seen in the next one, where we can find the terminal velocity is in a velocity versus time graph, because it will indicate a continuous acceleration in terms of gravity and the absence of drag. And since the item is subject to zero net force, the drag force pushes upward, and then the gravity pushes it downwards, which results in a balance. If we threw the ball downwards, would the terminal velocity be the same or different from the case as it was initially dropped from rest? From the left, we can see how it was initially dropped from rest with no drag and only gravity. In this case, initial downward velocity in the thrown scenario affects motion of dynamics because a non-zero initial velocity leads to a distinct acceleration phase and would actually go faster in the negative direction, so terminal velocity may differ, influenced by what the initial velocity affects. In conclusion, the purpose of this experiment was to examine how an object moves when dropped from rest while taking into account gravity and drag. Furthermore, the investigation of final velocity brought to light the importance of drag in opposition to gravity and its consequences on net force.